Lastly, here in question 4, we come to part D, which is back to being an explicit function. We want to differentiate y equals x squared plus 1 all to the power of x divided by x. But what we've got to recognize in this case is that the numerator of that expression has the form of a function of x to the power of another function of x. And the only tool we've got to deal with that situation is logarithmic differentiation. So although we haven't been specifically told that we need to use logarithmic differentiation, that's the way we have to proceed. So we've got y equals x squared plus 1 all to the x divided by x. And so under logarithmic differentiation, we'll start by taking logs of both sides. And remember, the whole point here is to now be able to simplify that right-hand side using the properties of logarithms, and we want to simplify it as much as we can. So the first thing we can recognize is that we've got the logarithm of a quotient. So properties of logs tell us that the logarithm of a quotient becomes the logarithm of the numerator minus the logarithm of the denominator. And now, the second term here, that's as simple as we can get it. But the first term, that's got that x as a power. That's how we recognize to use logarithmic differentiation in the first place. So properties of logarithms say we can take that x and we can bring that down front. So we've got x times the natural log of x squared plus 1 minus the natural log of x. And that's as simple as we can make this right-hand side, because the only thing we've got left here is that it involves the natural log of a sum, and there's no property that lets us simplify logs of sums. So now we're going to differentiate both sides with respect to x. And on the left-hand side, it's always the same for logarithmic differentiation. We'll always be differentiating the natural log of y, which by the chain rule, since the derivative of the natural log of x, as we'll use in a moment, is 1 over x, this is going to be 1 over y times dy by dx, or again, y prime if you prefer. On the right-hand side, we've got another instance of the product rule. So that's going to be the derivative of x times the natural log of x squared plus 1 plus x times the derivative of the natural log of x squared plus 1 minus the derivative, of course the difference rule applies here, minus the derivative of the natural log of x, which, like we already said, is 1 over x. So then that's going to be, well, the derivative of x is just 1 times the natural log of x squared plus 1 plus x times, here we need the chain rule, so we've got the logarithm of a function, so that's going to be 1 over that function times the derivative of that function. Minus 1 over x. So that's going to be, well, the product by 1 can go away because it doesn't really do anything. So we've got the natural log of x squared plus 1 plus x times 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2 times x. And then still we subtract the 1 over x. And there's the calculus done. But we've got a couple of things to do. We've got to clean up, simplify wherever we can. And we've got to realize that what we just found is not the derivative that we're after. It's 1 over y times the derivative. So dy by dx then, if we bring that y over, it's going to be y times this stuff. So y times the natural log of x squared plus 1 plus 2x squared over x squared plus 1 minus 1 over x. And then we should always substitute back in for y. This didn't start out as an implicit function. We had to make it 1 in order to be able to differentiate it. But if it starts off as an explicit function of x, the derivative should only have x in it as well. So this is going to be x squared plus 1 to the x all over x times this expression. So times the natural log of x squared plus 1 plus, just squeeze it in here, 2x squared over x squared plus 1 minus 1 over x. There's our derivative. And that's as far as we need to go in terms of simplifying. We don't need to find the common denominator of the terms in here or anything like that. We don't need to multiply this through. That's a perfectly reasonable way to leave the result of this logarithmic differentiation. We'll move into question 5 in the next video.